Some rational functions have the potential to create vertical asymptotes. And vertical asymptotes occur when the denominator is made to be 0 by plugging in a particular input value. Now we would exclude those values from the domain, but we might still want to talk about the function behavior near the vertical asymptote. Let's look at a very simplistic version of a rational function with a vertical asymptote. F of x is the function 1 over x minus a raised to the power of n. Now n is some natural number, 1, 2, 3, etc. And x minus a is the factor in the denominator that's causing this vertical asymptote. If we were to plug a into the value for x, we would get a minus a, and that would give us a vertical asymptote because our denominator is equal to 0. Now the behavior of the function around a vertical asymptote completely depends on the exponent that we have in this denominator. If that exponent n is even, then we have a behavior that looks like the graph that we see on the screen. We have a dashed vertical line to represent our vertical asymptote, and the function is drawn in green. In this case, the behavior of the function is identical on the left and the right-hand side of the vertical asymptote, and as we're approaching the vertical asymptote, our function outputs are growing to be infinitely large. So if we are talking about a function that follows this format, 1 over x minus a raised to the power of n, and we want to talk about the limit as x is approaching that vertical asymptote at a, we know that if n is an even integer, that this limit is going to be equal to positive infinity. Now, we see the two-sided limit here on the screen, but we could decompose that and say the left-hand limit is equal to positive infinity and the right-hand limit is equal to positive infinity. So we aren't checking one at a time, but technically we are, because we have to match the left and the right in order for the two-sided limit to exist. Now what about if that function, f of x, has an exponent in the denominator that is odd? So rather than an even exponent, what if we have an odd power down there? Well, that produces different function behavior. In this case, the function would look like the second graph that you see on the screen. We have the vertical asymptote in a dashed line, and the function is in green. In this case, as x is approaching that vertical asymptote, our function behavior is opposite on either side of the asymptote. From the left-hand side, the function goes down to negative infinity. But from the right-hand side, the function goes up to positive infinity. So in this case, if you're talking about a function that follows this format where we have an odd exponent in that denominator, then our left-hand limit goes to negative infinity and our right-hand limit goes to positive infinity. We can use these facts to help us evaluate our limits just by looking at the format of the function and identifying if we're talking about a left or a right-hand limit or a two-sided limit. In our first function here, I can see that we're following the format from the previous slide, and we're approaching that vertical asymptote at 4. We have an even exponent, which means the two-sided limit exists, it's equal to infinity, and so therefore the left limit is infinity, the right limit is infinity. All three of these limits, left, right, and two-sided, are infinity. If you have a function like this and you apply that theorem where we just look at the exponent and determine what the limit is equal to, then we can kind of reverse the logic and say we must have a vertical asymptote at the location where we are allowing x to tend to, meaning there's a vertical asymptote at 4. Let's take a look at the other function. In this case, we have an odd exponent, and from that previous slide, the theorem tells us approaching an asymptote where your function has an odd exponent on that factor in the denominator, the left limit is negative infinity, the right limit is positive infinity. Since the left and the right don't match, the two-sided limit does not exist. And again, we can reverse this logic and say if these are the limits that we're looking at, then the graph must follow this form where the function's behaving in opposite ways on either side of the vertical asymptote, and we're approaching -2, which means our vertical asymptote exists at -2.